In physics, heat and entropy are linked. As temperature drops, particles slow down, and the system reaches a stable, low-entropy state. Because temperature is a key parameter in large language models, developers naturally carry over this physical intuition. The standard assumption across the industry is that setting an LLM's temperature to 0 will strip away uncertainty and force it to be factual. But that assumption breaks down at the mechanical level. Dropping the temperature to 0 makes the model highly deterministic, but it does nothing to improve its understanding or fill in missing context. Giving the model a vague prompt at 0 temperature does not eliminate the ambiguity. You simply guarantee that the model will return the exact same hallucinated or incorrect answer every single time you press run. In the architecture of neural networks, the temperature parameter does not control system entropy. Setting it to 0 merely masks the chaos without curing it. To see why, we have to separate how the model evaluates text from how it outputs text. Temperature operates strictly at the sampling layer, meaning it only dictates how tokens are selected, not how they are scored. This animated diagram shows a model's underlying probability distribution, mapping the logits. These are the raw mathematical scores assigned to every possible next token. Notice that the curve itself remains completely unchanged regardless of the temperature setting. At a standard high temperature like 1.0, the sampling algorithm behaves stochastically. The selector is allowed to jump randomly across the curve, picking from various high and low probability peaks to generate creative variations. When you dial that temperature down to 0, you execute a very specific mathematical function. The sampling algorithm is forced to rigidly lock onto the single highest probability peak, completely ignoring all other options. We call this collapsed output variation. Forcing the model to pick the highest peak does not mean that peak represents a high confidence choice. The top token might only have a 15% probability of being correct, while the next 5 competing tokens sit at 14%. The ambiguity and uncertainty remain mathematically present in the system's calculations. The user is simply blinded to it because the model is no longer permitted to show its varied internal state. Lowering temperature does not eliminate model uncertainty. It only collapses output variation, creating the false illusion of a highly confident system. This problem compounds exponentially when we move from predicting a single token to generating an entire reasoning path based on a weak prompt. This chart maps out a high-entropy decision tree created by an ambiguous context window. When that context is weak, the model generates dozens of fragmented paths, where correct and incorrect reasoning steps have nearly identical low probabilities. Faster, more urgent tone. When you set the temperature to 0 in this environment, you force the model to traverse this highly ambiguous tree by blindly taking the marginally highest probability branch at every single node, regardless of how close the margins are. If the initial reasoning path diverges into a factual error early on, the deterministic nature of a 0 temperature setting ensures the model is trapped in that flawed logic. It will march straight down the wrong path until the generation is complete. Engineers observing this behavior often assume the model is broken or incapable of handling the task. In reality, the prompt created a hallucination, and the 0 temperature parameter is just executing that hallucination perfectly on every run. Applying 0 temperature to a weak context window does not solve hallucinations. It simply hard codes a consistent reasoning path of consistent mistakes. Real entropy reduction requires altering the underlying system state, the context window itself, rather than manipulating the sampling algorithm after the fact. Let's look at the static multi-peaked probability distribution from earlier. This animated diagram shows a state of high ambiguity, where many potential tokens are competing for selection. By introducing clear constraints and relevant contextual data into the prompt, we alter the logits. The math shifts, suppressing the probabilities of incorrect tokens and squeezing the distribution inward. These specific structural inputs force the target tokens into an overwhelming mathematical dominance over the rest of the vocabulary. The ambiguity is eliminated at the source. Once the probability space is narrowed to this degree, the model becomes naturally reliable. The top token is now the obvious mathematical choice, even if you leave the temperature at a higher, more creative setting. True precision requires narrowing the probability space before the sampling phase ever occurs. The primary tool for shaping this probability space is what we call structured communication. A common misconception among developers is that structuring an output simply means appending the phrase "respond in JSON" format to the end of a prompt. While JSON is highly effective for machine-to-machine data pipelines, forcing a strict JSON schema can actually hinder a model's natural language reasoning capabilities if the underlying ambiguity of the task hasn't been resolved first. True structure organizes information to explicitly eliminate ambiguity. A structurally sound prompt organizes the request into 4 distinct blocks: task, context, constraints, and output format. Clearly defining constraints, such as instructing the model to avoid jargon or limit to 3 bullets, acts as a negative prompting mechanism. This instantly zeroes out the probabilities of vast swaths of irrelevant tokens. For complex reasoning tasks, natural structured language is often vastly superior to code-based structures because it aligns much closer with the massive corpus of text the model was primarily trained on. Structure provides the necessary framework to reduce the model's internal uncertainty. Achieving advanced reliability requires a total shift in how we approach these systems. We have to stop treating large language models like closed thermodynamic systems, where freezing the output parameters guarantees an orderly state. The definitive rule for tuning your applications is this: temperature handles output variation, but structure handles system entropy. A model operating at a high temperature with a highly structured prompt will consistently outperform a model operating at 0 temperature with a vague prompt. You cannot cool a large language model into correctness. You must guide it into clarity through rigorous, structured context.